using cost Malmquist, I realized that for the productivity index, aside the two-stage decomposition, it can also be subdivided into four stages.
We are
That is
coming to
the,
that. We have not done that.
I wanted to ask if it's for only cost or for the normal activity index also it can be further
Normal
broken.
Malmquist, we have two-factor decomposition. You have three-factor decomposition. You have four-factor decomposition. And I think I showed you that the other time. But majority of people don't talk about a four-factor decomposition. It's by Wheelock and Wilson and Simmer. Many
Okay, Doc,
talk
thank you.
about it, but it is there. Yes, you get it.
Yes, please.
Yeah, it's there. So what I want you to do is that in your own example that you'll be doing, I want you to make sure that the blue line and the red line will intersect, or one side will be bigger than another. You know, in other words, it's not supposed to be, the distances are supposed to be the same all through. So just know that if they cross, the better. If they cross over, is the best. So that is what I want you to do. Now let's go to the isocost. Let's put the isocost and the isoquant. Now, you guys already know how to estimate the isocost. We did that when we were doing cost efficiency. So if you look at just the year zero, the cost efficiency, the marginal cost efficiency is the isocost, which is parallel to the potentially so-called isoquant, which is the blue line. And then we do the same thing for the year one, which is for the red line, the red isoquant. And then you also have its own isocost. Nothing else. Now, the way the isocost is looking like, the way these isocosts are looking like is as a result of some approach that we used, the tones approach that we used. So keep that in mind. Okay, it is from that this is happening. All right. And by the way, note that you are estimating these efficiencies and these cost productivities using tones approach of cost. Using tones approach of cost. So keep that one too in mind. Sometimes this, for a simple example like this, the tones approach will lead to the Farrell and Fair approach. Okay, for example, but for larger data set, it will not lead to the same results for every firm. So keep that one too in mind. All right. Now I've done these computations and I've put some radial lines and some zigzag lines through. And so we are going to just do that. Okay. So let's start. First, we need to understand the cost. The Maniadakis and Thanassoulis cost productivity. They were the ones they looked at the normal Malmquist, which is by Fair, Groskov, Lengren, and Roos. That's the first Malmquist, which was extended to Fair, Groskov, Norris, and Zahn. Okay, and I think 6 years later. And what they did was to extend this into estimation of cost productivity, especially when the data on cost are available. And you guys are going to see that the reason why this extension is needed is because there may be some allocative element. There may be some allocative efficiency element that are there, and we need to know the source, the true source of productivity. And in the process of capturing the true source of productivity, we need that. We need that. We need that. So it's very important to decompose it and get to know the sources. The two-factor decomposition is overall efficiency change and then cost technical change. And you can decompose the overall efficiency change. To be honest, I would have wished that it was called cost efficiency change. That is how I would have wished it was called, cost efficiency change. And actually, you can also decide to call it that, cost efficiency change. So that it sounds nicely like cost efficiency. The other one was technical efficiency change. Okay. So this one becomes cost efficiency. Then the other one was technical that one will technical change, which is the second part. And this one become cost technical change. You know, so it becomes all nicely done. Cost technical change. Anyway, now the cost efficiency change, which is the first part, you can split it into the efficiency change and then the allocative efficiency change. Okay, or what is known as the technical efficiency change, the allocative efficiency. All of them are capturing the cost side. Okay. And then, of course, you can have the cost technical change. I've not explained that the cost technical change can be split into the cost technical change and then the price effect. We'll come and talk about that. Okay. The allocative efficiency change, sorry, and then the price effect. The allocative efficiency change and then the price effect. So those are the two main extra things that are added to the original efficiency change and the technical change. Okay. They are the allocative efficiency change and then the price effect. Now there's something you need to quickly know. Why does somebody have to estimate the cost Malmquist? It's simple. When the producers are cost minimizers, input prices are known, you can do that. In other words, when you have data on input prices. Okay. And in this context, you define everything in terms of cost instead of in terms of quantity. Okay. So we are dealing with more of cost distance functions. So the radial distance is towards, you are hitting a cost boundary. You are not hitting a distance boundary. You are not hitting an ISO cost, but you are hitting an ISO cost. A cost boundary, but not a production boundary. And of course, there are some formulae that you're going to understand here. So let me quickly go through something you already know. The normal cost efficiency is this. We call it overall efficiency. That's another name for it. The standard cost efficiency is this. And in this context, we are putting it as if it's in year T. And this cost efficiency, or the overall efficiency, is defined as the minimum cost over observed cost. You know this. The minimum cost over observed cost. Now, watch the second part. It's very important. And I think I showed you this thing the last time we were doing cost efficiency. Cost efficiency is this part there. The CWY is a cost efficiency. I could have added X there. This part here, that is a cost efficiency. If I multiply this one by this allocative element, and by the way, this one is the observed cost. This is the observed cost. If you multiply it by that and divide it by the distance function, you are going to have this same cost efficiency coming out. Now look at this part here. That is a distance function. That is more or less like the technical efficiency if you were to take the reciprocal. So if I want everything to stand alone here, if I want CT to stand alone, I will multiply this denominator by the AET and then divide all by the D. And that will give me this cost. Now multiplying the denominator, which is observed cost, times the AET, multiplying the two of them, okay, that will give you something which is known as pure technical efficiency and more or less a scale efficiency. And this is very important. So let me just go over it again, because other than that, you may be slightly confused. So cost efficiency is the technical times allocative efficiency. We know this already. The technical is split into pure technical and scale efficiency. Pure technical and scale. So if I should have allocative efficiency, this one here is allocative efficiency. Now watch this part. The CT over the WXT. The CT over the WXT. This part,
Yes.
let me just circle it slightly because I want to make a point. Okay? And these points are important. Oops. So this part here, what I want you to do is to watch this part there. That part is a cost efficiency. So if I should pull that one out, we will have this as cost efficiency. And this is multiplying something called what? The reciprocal of the technical efficiency. Watch. Watch. Now, this dt that you are seeing here, it is 1 over t. Is the reciprocal of the technical. Do you know that?
Yes.
So it means that the whole of what you see there is equal to c over t, which means that you can now multiply this te by that, and that gives you c to be equal to te times a. And that is what you have at the top here. That's what you have at the top here. So that is all I wanted to understand that about this. And these terminologies are very important because when we start going into calculation of the cost, you will appreciate it much. All right. So let's move on now. Okay. And all of these things that you are seeing on your screen are things I've already shown that you're going to. Now, how do you estimate cost? How do you The cost productivity is estimated the same way as the technical productivity. It's very important you understand some key words. It uses the same approach of the two distance functions, the two productivities of Cave's approach, or CCD. And it's having the same kind of distance functions. So when you can see that we have some kind of, not distance function, but in this case, cost is there. So you have two kinds of distance functions, more or less. The one related to the cost frontier and the one relative to the production frontier. So that's what you see right there. And I want you to understand some key thing here. Forget about the top part because we brought it together here. Look at the CMPI, the actual one at the bottom here. Okay. When you look at the actual one at the bottom, you will notice some key points that should guide you. One, you will see that the first part here, it is CTCT. Do you see that? And the second part here is CT
Yes.
plus 1, CT plus 1. Do you see that? Understand that first part. It's very important. So the first part, and that's what is important. You see, the other angles that are here, left and right of it, are not important much. What is important are the CT, one top, one down, and then the CT plus 1, one top, one down. Do you guys get it?
Yes, Doc.
They are the boundaries. They are the boundaries. Okay. And that's with that in mind, okay, that is how you are going to estimate the cost Malmquist Productivity Index. Now, as for the WX, we know that already. Okay. We know that we've defined it as the observed. That's how we called it. The observed cost. The observed cost. Whereas the one with the C is the minimum cost. Is the minimum cost. If you estimate the productivity, and because we are using input, because it's cost, we want to minimize it. Because we are dealing with minimization, anytime the value is less than 1, it is progress. And anytime it is greater than 1, is regress. We know this already. Anytime it's equal to 1, is constant. Progress is the same as improvement. Regress is the same as deterioration or decline. And then constant is the same as stagnant. But of course, given the inverse property and the duality that we know, and the fact that most of you will be using the MaxDA software, the score will nicely be done for you, and a score less than 1 will rather be regress, and greater than 1 will rather be progress, and all of that.
Doc, please, I have a question.
Yeah.
So when we're looking at the technical Malmquist, we realized that we used two on periods and then two cross periods
Yes.
results to calculate it. But for the costs, I'm
Question
finding
is
it
that the
difficult
same thing
to.
here?
Yes,
Okay.
is it the
So
same?
let's go back and then you see. Okay. If you look here at the CT plus 1, do you see CT plus 1?
Yes, Doc.
The one I'm showing here. Okay.
Yes.
You will see that everything on the index, sorry, on the exponent to the power,
Yes.
everything in the power are t plus 1, t plus 1, t plus 1, t plus 1. Do you see that?
Yes. Yes,
And when
Doc.
you come down here too, on the bottom left,
Okay.
left one, the bottom, everything on the top is t, 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 t. Do you see that?
Yes, Doc.
They are their own periods. Okay. Now, when you go to the other ones, you see that there is a mix of between t and t plus 1.
Yes.
And then if you go to this one, so there's a mix of between t and t plus 1. Those are the cross periods.
But Doc, how do you compute that?
Oh, we are going to compute that. That's why we are here.
Okay, Doc. Thank
All
you.
right, okay. That's why I say pay attention to understand how they are computed. Okay.
Yes, Doc.
So these are the graphs now. Again, we are going to maintain the same distance function principle. Do you guys get it clear?
Yes, please.
Yes.
We're not going to change anything, just as we did before. So keep that in mind. And remember that in the previous one, we were estimating them relative to isoquant. Okay, let me just show you something about it. In the previous one, we were estimating everything in relation to the blue frontier or the red frontier. But when it
Yes.
comes to cost, we are simply estimating them relative to the zigzag lines, the isocost lines. That's all for cost. Do you get it? I'm going to do an example, but what I mean is that do you get it when I say I'm estimating it relative to the isocost?
Yes.
All right.
That's the answer.
So we're going to take a couple of examples. Okay. Let's take the original Malmquist, this one. This one. Now, I told you that this red one and this red one, they are all own period. Do you remember?
Yes, Doc.
Okay. So we are going to do for the same DMUE. So this own period here, we are going to estimate the efficiency of DMUE, sorry, the distance function of DMUE relative to that cost boundary, relative to that very cost boundary.
Okay.
You might be sitting down in your corner somewhere, and then you might be asking, what do I mean by that very cost boundary? Okay. So let's go to the graph. This is a graph. And we are doing it for E0. Oh, what is the cost? Let's look at the cost boundary. That was year T, isn't it?
Yes.
Let me just check. So that was year T. Okay. So year T. So we are going to estimate for. Okay. I'm doing the down one. Oh, I'm doing the down one and not the top one.
Okay.
So in doing the down one, we are going to estimate the kind of cost distance, not distance function, but a cost distance for E naught. So let's go to the E naught. So this is the E naught, and the cost distance should be the marginal cost 0, not the marginal cost 1, not this one. Are you with
Okay.
me so far?
Yes, Doc.
Yes, please.
The 0, 1. So normally, this is how we define the efficiency score. We define it as a distance to the firm, this time because it's distance firm. Distance to the firm divided by distance to the frontier. Is that not so? So distance to the firm is OE naught. Do you guys see that?
Yes.
Yes, please.
Distance to the firm, distance to the cost frontier will be what?
OG.
OG.
OG. Very good. So let's go and check that. Okay, let's do that. So do that somewhere. Do that. You guys should do that somewhere. I don't want to show the answers, but I want you to see the formula. So that is the one we've done for the down one here. So right for the down one is going to be OE naught over OG. Can we proceed? Can we proceed to the right diagonal one, the numerator on the top? Dan, are you with me?
Yes, Doc.
Can we proceed?
Yes, please.
All right. So we are going to do for, now because we are in T plus 1, we are not going to do for E naught. We are not going to do for EO. We are going to do for what?
E1.
E1, good. So now go to E1. Go to E1 and you're going to estimate it relative to its frontier there.
Okay.
And when I say its frontier, I mean its cost boundary. Its cost.
Cost.
Good.
Okay.
So what would the distance be? We're talking about E1. So it's going to be what? E1 happens to be
E1.
the corner. So to be distant to the firm E1, so that will be OE1.
Yes.
Divided by
OE1.
Good. Divided by OE1. But since B1 is here, we could also say divided by what?
OB1.
Good. Do you all agree with that?
Yes, please.
Okay. So that was just coincidental. That was just coincidental. That E1 happens to be, the cost boundary happens to be at the same point as the frontier. So with that in mind, write that one down for this one. For this top one here.
Okay.
That's what you have there. Can we proceed now?
Yes, please.
Okay, now let's go to this cross periods. The most difficult aspect is the cross periods. Now, when you look at the cross periods, let me just somebody will say, let me just be absolutely clear. It's cross. And so the firm, the more or less like the current year, or how do I put it? What is this? I'm looking at the top one here. The current year is the CT.
Yes.
Okay, so the CT becomes, suppose I'm talking about year 0 and year 1, the CT is the year 0.
Yes.
Okay. And then when you come to the bottom diagonal one here, the CT plus 1 will be the year 1.
The year 1.
Now, because this one is the year 0, we are now measuring something relative to frontier, relative to the cost frontier in year 0. Do you get it? In year 0.
Yes, please.
When you go up here, the cost frontier in year 0 is the MC0. This one, isn't it?
Yes, no.
So have it in mind. We are going to measure something relative to that. But that something shouldn't be that something in year 0. It should be that something in year what? 1.
Year 1.
Good. So it is that something in year 1. That is why you have the XT plus 1 here and then YT plus 1 there. Do you get it?
Yes, no.
Now, when you go to this formula, the second formula on the bottom right, you will see that you have XT and then YT, not T plus 1s. Do you see that? It will be the opposite. Yes. So this T plus 1s are what so we're going to pick the firm in year 1, not year 0. So that will be E1, isn't it?
Yes, sir.
So we're going to do the efficiency, the cost efficiency more or less of E1 relative to the cost boundary in year 0.
Yes.
What would that be? What would that be? It's obvious.
So, yes.
OE1. That's for the firm. Over what?
OB1, OB0.
over O
Over what?
OF.
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 It's going to be OE1 over OF. Of course, that OF, it just happens that it is the same as the BO. But I don't want us to use the BO because, you know, other than that, you might be confused of the isoquant and the isocost.
Okay.
Yes, so it's OF.
Okay.
And that would be this formula here. That would be the top part here. Can you all do the last one here for me? Now do the last one at the bottom right here for me. If you want to know, let me just guide you. Okay, oops. Let me just guide you. Remember that we are now measuring it relative to which frontier? Which cost boundary?
The
0 or 1?
Boundary 1.
one.
Cost boundary 1. Okay, and you are dealing with the E in which year? Year 0 or year 1?
Year zero.
Year 0.
So E in year 0 relative to the cost boundary in year 1. That's what we are doing.
Yeah.
What would that be? In year 0 relative to the cost boundary in year.
Okay.
So, Doc,
Or in this case, the year 2. Yes.
so Doc, that would be OE0 divided by OH.
Excellent.
Yes.
Now, because OH is where that radial fraction actually cut the cost boundary for year 1. Year 1 cost boundary. Do you guys see?
Yes, please.
Now, one of the things you guys must know now about me is that I'm the kind of person who is very detailed so that you see what is happening. It's not just picking things. But you got to be seeing behind the scenes what is really happening. So it is going to be OE0 over OH. Now, why did I put OH there? Because I put OH there. I put an H there because I'm expecting something to happen there. So when you guys are creating your own hypothetical data, you got to know where you are going to put what there. If you don't put what there, and then you have to trace it downwards. You have to pick it downwards here. Now, of course, in your own, if you're going to do hypothetical, specific, detailed analysis like this, you must have calculated the whole thing and put them down. And then the software will guide you about where what should be. I'll tell you very soon what I mean. Where what to be. Because how did I know that the value is 3.28? Do you get it? How did I got it because when I estimated the cost productivity from the software gave me some results. Okay, let me just show you something. This is not exact results though, but let me just hope I can show you something here. I just want to show you something quickly about this. So let me just, I'm showing you the MaxDA software. And I'm just going to run the model. Let me just run. This is not the same data. We'll come to the same data, but I'm just going to use something to tell you. Do you guys see the screen, by the way?
Yes, please.
So this is a cost type you choose. This cost type at the bottom you're choosing is the one that should be selected all the time. Then the orientation has been done already, is input oriented. Returns to scale, I'm going to just make it constant returns to scale. And then under the advanced models too, I'm going to use the normal Malmquist here. Okay. I'm not using a binary, I'm using the normal Malmquist. Now I'm going to estimate the results and then show you something. Now this is a result. Look at the Malmquist here. Now you see the Malmquist is giving me some values. Efficiency with 1. Do you see that thing?
Yes, please.
Efficiency score 2. That's the on period and cross period. Efficiency score 2 minus 1. Efficiency score 1 plus 1. Okay. and all of that. But this from here is the normal efficiency change, technical change, and then blah blah blah. Now, these values that you are seeing, this one, that one, okay, that one, those are the on period and the cross period efficiency scores. Okay, those are the on period and cross efficiency scores. Now, how do I get that value 3.28? Well, this is how I got it. Watch it something. Okay. Let me just go back to the data that I was showing you. Now here, I know that, first of all, I was doing OE0 divided by OH, isn't it? Right?
Yes,
Yes,
Doc.
yes, Doc.
I know that OE0, the E0 will give me a value of 3.5. Is that not correct?
7 points.
Sorry, 7.5. Is that not correct?
Yes.
Now, so I have 7.5 divided by H should give me a certain value, isn't it?
Yes.
Please.
Now, once I went to that software, the software gave me that value.
Okay.
The software gave me that value. And how do I know that the software gave me that value? Well, like I said, when you look here, let me just go back here. When you look here, the value is this. So I'm just assuming something. The value will be one of this because I understand what this part is showing. It's showing that cross period. So I know that the value is maybe 0.53. So now what I will do now is that I will do 7.5 over H equal to 0.53. Then I'll do cross multiplication to get the value of the H. And then I'll come and put that 3.2 there. Do you guys get what I mean?
Yes, please.
Because you can't easily pick it from the graph. There's no way. You can't easily pick it from the graph. But understanding will help you to get the exact value on the graph. So that is how I'm able to now pinpoint the actual values. It's a very beautiful exercise when you go through step by step and work it out. Does it make sense?
Yes,
Yes.
please.
So on the basis of that, that will give you that value, the cross. And so you are finally able to get all of this. Now check what you have, whether that's not the same thing here. Do you have the same thing? Because I told you to write it.
Yes,
Yes, Doc.
please.
Yes.
Yes, it's the
You
same
see,
thing.
so now because you did it by hand, you can now appreciate this value, this whole thing that you are seeing here. You can appreciate it. But you have not done it by hand. So again, Dinah, it also helps you to know that these values that you are seeing here, they look so confusing, but they are not technically speaking that much confusing. They are still made up of 4 different distance functions. These distance functions are cost distance functions. They are not technical distance functions.
Okay.
And if, for example, if you look at this top one, it looks so complex, so
Yes.
and yet it is just OE1 over OB1. So you don't have to be scared. And once you know these 4, trust that you know all the rest, because like I told you, the estimation of the cost distance is made up of 4 distance functions equally like this.
Okay.
It is the decomposition that will help, that will mean that we need to go and take some few things from the normal technical distance functions. The decomposition, okay? Because the decomposition, there's some technical change and then there is some efficiency change there. So we need to go and borrow some of the other ones from the previous ones.
Okay.
All right. Now, so here's the thing. I want to just pinpoint something about this OF because that one was a little bit confusing. If you can remember this OF here. So I decided to explain it. Now this OF, what is that? This OF, which also happens to be B1, this F and the B and the E1, they are usually on the intersection point between the radial line, through the isocost, both the isocost 1 and isocost 2. It is the intersection between the radial line and the isocost. So this is just for you to understand that it is the intersection between this radial line and the isocost, and it's not the what do you call it? It's not the isoquant. It's not the iso. It's the cost we are dealing with, and not the quant. And also, all estimations are relative to the cost frontier instead of the production frontier, or relative to the ISO cost rather than the ISO. So on the basis of that, you can now find the answer. I don't need to. It's when you know the values, you know the answer. Now, look at this one here. 2.1 over 2.1. We know this. Okay, 7.4 over 4.28. These values that you are seeing me write them in the slides, I had to get them after I've done the estimation, just so that it will be clearer. Because if you use your eye, you will not get the exact decimals associated with it. And then the rest is a normal simplification, and you take the square root, and that gives you 0.418. Now listen carefully. Listen carefully. The cost productivity is equal to 0.418. Take the reciprocal and tell me the score, and I want to share something with you.
Doc, is 2.392.
Again?
2.392.
Good. So that means that productivity, cost productivity has gone up by what?
1.39.
This has gone up by 139.2%.
139.
Yes, 0.2%. That's the growth.
So you can see that normal technical productivity for DME was up by 114%, isn't it?
Yes, please.
And now cost productivity has gone up by more, which is what?
139.2.
What does that tell you? Does that not even tell you the more reason why you should consider cost productivity? In other words, a firm has to be cost efficient, more cost efficient than just being technically efficient. In other words, the allocative aspect of the firm has to be considered. You see, whatever that is making this particular kind of productivity to be high, it's not coming from efficiency. It's not coming from technological change. It must be coming from another source beyond these two, and that source is what? Allocative and the price. So that is why this is just a bit of an interpretation to help you know that cost productivity is beyond technical productivity. Cost productivity is beyond technical productivity. Okay, can we proceed?
Yes, please.
All right. So now you know this. Let's go into the decomposition. Now, this is just a graphical interpretation of the decomposition. That the cost productivity can be decomposed into the overall efficiency change, which I said it should have been cost efficiency change, and then cost technical change. Now, and that's a two-part decomposition. The four-part decomposition is that the overall is split into allocative efficiency change and then its technical efficiency change. Now, this very same technical efficiency change is what we normally use, plus this technical change to get the normal Malmquist. Do you guys see that?
Please.
Okay. And then the cost technical change here, there's a part here. Now, guys, let me tell you something. When you are going to do any of your analysis, you got to do this. You got to do this, and then you got to find each of these two parts and then the four-part decomposition and fish out the Malmquist as well. And fish out the Malmquist as well. Because at the end of the day, there's something beautiful, something interesting with this so-called maze that you see there. Now let's proceed. So let's look at the first decomposition. Remember, always have this chart in mind. Overall efficiency change, cost technical change. Okay. Now, this part is interesting. Let me tell you why it's interesting. Because it is bringing some aspects into it. This is the decomposition, by the way. Now, Dinah, if you look at this, even though this might look quite complex, is it that complex? Guys, is it that complex?
No, not really.
Because we know where these ones are coming from. Remember, the numerator here is a own period over own period, which we know
Yeah.
normal technical productivity, it would have been the efficiency change, but here it is the overall efficiency change. Now, that same value here is the same value you have here. Watch it. That same value at the numerator is the same value you have in the first part that is denominator here. This same value that you have here as the denominator, EC, it is the one you have on the cross far right here. The cross period are these two, which are the kind of the demand function, demand curve. Like, are you guys with me?
Yes.
Yes, please.
So it is picking the same values and dropping them here. Is that also?
Yes.
And by then, watch it. Let me not even go too far. By then, you know all of these already. So you are just going to pick from here. Not even there, even here. You can pick it from here. These four. You can pick the answers here. Because you know what the 0.7 here mean. You know what the 1 here mean. You know what the 1.57 blah 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 here mean. You know what they all mean. So you just drop them. But then I decided to still go through the same gimmicks. Like this. Drop, 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 and finally, you get this. So now the cost productivity has been decomposed into overall efficiency change for E and then the technical change. Let me end with this. This is the actual, what is it? The actual answer. Now, of course, you have to take the reciprocals again. Okay. And then you have to tell us, so what is driving cost productivity for E? What is driving? Overall efficiency change?
Overall efficiency change.
Yes. It is increasing the cost productivity by how much?
By 75%.
Okay. So the actual value was 1.75, eh?
Yes, 1.75.
So by 75%. And then the technical change, the cost technical change was increasing productivity by how much?
37%.
Exactly. So you can see that the overall efficiency change is doing more than the cost technical change. Now, first of all, listen, pay attention. So from here, we know that the overall efficiency change, the top part here, is doing more than the cost technical change. Now the question becomes, this overall efficiency change, which is doing more than the cost technical change, the value is bigger, almost twice. So what is driving this overall efficiency? Is it the technical efficiency change or the allocative efficiency change? Because we know that something is driving this overall. Is it the allocative? Now, can it be the technical? No. The reason why it cannot be the technical is that in this very context, we got to know when we estimated the normal technical productivity, we got to know that what was driving that normal technical productivity. What was driving it? Anyway,
It was the EC.
if, if you
It
can see,
was the efficiency change.
it was efficiency change. Okay, it was efficiency change. And so the temptation will be that if it is this efficiency change, then that must be driving this. Could that be the case? So that is why we need to know the components of the overall efficiency change to see what is really driving it. We need to get to know the sources. You see, once you get to know that there's something you are good at, you power there. If you are not good at football, don't go and power in football. You're good at volleyball, power. Anyway, so let's now go to the cost technical change. This one, the CTC. That one too is split into technical. I don't know why I wrote TE, but it's supposed to be TEC. Okay. So that one is split into cost technical, sorry, split into technical change and
Yes. Price effect.
okay, But first, let's look at allocative efficiency change. The overall efficiency change. So this is overall efficiency change and is made up of the technical efficiency change and the allocative. Now watch carefully this. The technical efficiency change, it is the same thing that we had from the previous Malmquist. Do you remember the previous Malmquist?
Yes.
Yes,
Watch it
please.
here. It hasn't changed. So that one, you pick it from there. But the allocative efficiency change, it is tricky. It is tricky, but it's not tricky. It's tricky, but it's not tricky. Don't go and die. It's tricky, but it's not tricky. Now, one quick thing I want you to notice that in this very context, there is no square root. The overall, the final four-part decomposition of the Malmquist, the cost Malmquist, there is no square root. Okay, so fine. What are we going to measure against? Now, first thing, you should know this CT plus 1. You should know this CT plus. As for these other ones, we know them. The key point is know where the C is. Now, you see where the C is where the D is. They are all having T plus 1, T plus 1.
Yes.
And you see where the C is and where the D is, all having TT.
Yes.
So, now this value here, this CT plus 1, we've got it. We know it already. Yes, Chris.
Sorry, please, was a mistake.
Sorry?
This was a mistake. The reason of the hand. Sorry.
Okay. So we know this CT plus 1, all that aspects into the bracket. We know it already. How do I know we know it? Well, we know it because we calculated it before. Okay? If you go up somewhere, you will get it. You know that.
Yes.
You get this thing. CT plus 1, YT plus 1, WT plus 1. You will get it. Okay. Let's just jump so you see that here. This is it. CT plus 1, YT plus 1, WT plus 1 is here. Is here. So the whole thing is going to be OB1. That is for the OB1.
Mm.
We don't have here is that this part here has been slightly mixed. But don't worry, we'll get that. So let me just go down. Now the part here, you see that it's also what? It is also WT plus 1, XT plus 1. You see that?
Yes.
Well, if it is WT plus 1 and XT plus 1, then we have got it. It's the same thing here. Is that also?
Yes.
It's the same thing up here. So it's the OE1. However, watch the formula carefully. It is not like that part divided by this part. No, it's divided by this part which is already multiplying something. Something is this. It's a distance function relative to the production frontier. So you just have to know this value and then that value, multiply them before you come and divide this one by that. Do you get what I mean?
Yes, please.
Yes. And once you do that, and you do the same thing for this, remember they are all t at the down here. They are all t plus 1, t plus 1, t plus 1, t plus 1 at the top. And so it's very, very simple. Once you substitute, you will get the allocative efficiency change. Let's do that. So this is the part there. And there's even another way of calculating this allocative efficiency change. There's another way of calculating this allocative efficiency change. And that way of calculating this allocative efficiency change, apart from what I've just shown you, is this. OE1 over OB1. I want you to see something because remember that allocative efficiency change takes into consideration, take note, it takes into consideration the gap between the cost boundary and then the production boundary. Take note. The gap between the cost boundary and the production boundary. So look at OE1 over OB1. Let's go to the graph and let me show you something. OE1, this is OE1. And the other one is what? OE1 over OB1. So that would be kind of 1 over 1. Isn't it? OE1, oh sorry, I said is the gap between the cost
cost
boundary
boundary.
and the production boundary. That's what I said, yeah?
Yes, Doc.
Yes, it doesn't change. So the gap between the cost boundary for E1 and then the production boundary for E1 is at the same point. So the distance will be OE1 over OB1.
Okay.
Sorry, OB1 over OE, where the B1 is for the cost and the E1 is for the production. And the answer will be what? 1.
1.
Now the same thing, okay, when you look at this one, again, it's going to be that the distance between the cost boundary and the production boundary. So if you look at this, the E naught, see the E naught, the E0. And then again, the E0 is in the production frame, okay, and the boundary for that is C naught.
Yes.
And then the boundary for that year 0 is J. All of them are in year 0.
Yes.
We're looking at the distance between the J and then the CO. So let's go down and see the formula there. Okay. You see the distance between the OC0 and then the OG. Does it make sense?
Yes, please.
Yes. So this one will be 1 over 1. And then what about this? Before we see the answer, what do you think this one will be?
Is it to be 5 over 4.28?
Exactly. So that is how it's going to be 5 over 5, 4.28. Now you can use this part or you can use this part to represent it. Okay. This part I think is easier if you know that it is a gap. That's a key. If you know that is a gap. So when you do this computation and manipulation, you now be able to get the overall efficiency change where it is coming from. And the answer will be 0.667 and then 0.8 blah 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 blah. So on the basis of this, and going back to the answer you gave, Dinah, you will see that the overall efficiency change is being driven by what? The technical efficiency
By
change.
the technical efficiency.
Exactly. It's being driven by the technical efficiency. Does that rule out the allocative efficiency change? No. But it just shows that now we know that it's not being driven by the technical efficiency change 100%. A certain percentage is also being driven by the allocative. And that helps you to know that you cannot exclude allocative elements. When you are writing your essays and using those things to interpret what is happening, these are some of the things you need to really be showing. It's not a matter of just calculating and sleeping. It's a matter of interpreting what you have.
Okay.
So that is how you calculate the overall efficiency change. Now let's go to the last one. Oh, by the way, this is interpretation. Okay. It shows an improvement in allocative efficiency. An improvement in allocative efficiency of DMUE between 1 and 2, since the allocative efficiency part has risen from 0.856 to 1. You can see that it's risen from that. If you look at the value here, look at it. Okay, where is that? 0.856 0.856 to 1. Now, how do we know that to 1? Well, you can see it from the graph. If you look at the graph carefully, you can see that the movement was 1. Was 1. If you look at it carefully, look at it from here. Okay. The movement was 1. Look at this one. It is 1 divided by 1. Okay. And then look at this one. You can see clearly that there is a figurative number from that. But the graph actually makes it better. Okay, let's look at the graph. The gap here between G and C. You can see that there is a gap. Okay. And then if you look at this one here, there was no movement at all between the cost boundary and then the production boundary. But here, you see that there's a movement from the cost boundary. In terms of movement, there has been an improvement. And of course, this one is showing that sort of improvement. When the DMU moves from year 1. Now, before we calculate the price effect, which is the last one, I want to show you something. I don't want to give you the interpretation until. So let's look at the last one, the price effect. Again, this price effect can collapse you depending on your mind. It can collapse you. I won't lie to you. But again, Diana, don't be confused. This is the same.
Yes, Doc.
This same technical change is what we had before. So let's drop that one. We know this from the production, technical productivity. Now this part here, we have seen it before. Watch it. Watch it. We have seen this part here before. Now the CT, blah, 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 we've seen it. It's a matter of picking everything relative to the CTs. I told you that forget about the other ones here and focus on what? The CTs. And then the DTs. The CT plus ones and then the DT plus ones. And that's what you are going to pick. Let's take a typical example. Let's take an example of CTW, blah, 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 blah. What's the name? You get what I mean? Let's take an example. An example which is, by the way, as for the WXT plus 1, you know this. You know this.
Yes.
Okay. That is the firm, we use the X. That is a firm in year T plus 1. So if you firm E in year T plus 1, okay, firm E in year T plus 1 is what? That's OE1.
Yes.
Okay. So we expect that this one here, this top part here will be OE1. Now this CT and YT, forget about this distance function. We know this distance function. Okay. This CT here, what would that be? Okay, this one. Now look at what is inside. What is inside here was a second year. Isn't it? Was a second year. Watch it. YT plus 1. That is the second year, isn't it?
Yes.
So just as this XT plus 1 was the OE1, this one here is the OE1. But relative to which frontier, which cost frontier?
The
Period
zero.
zero.
The year
Frontier
0.
year.
So you are going to look at E1, okay, and then the cost frontier year 0.
Okay.
So you are measuring the distance function of firm E1 relative to cost frontier 0. Okay, let's go up and see. Cost frontier 0 is what? If you look at E1 relative to cost frontier 0, is it what? Is it not OF?
Yes.
It's OF.
Yes, Doc.
Okay, but then remember that the way we do it is, if you look at this, sorry, let me just go down. If you look at it carefully, it's multiplying. These two are multiplying each other.
Yes.
Do you realize that? If you don't take care, you will not realize that. I just want to be sure that you guys are with me. Yeah, this part is a little bit. Now, let me just do this so that you see it from here because it's tricky. What this means is that you are estimating the thing relative to the CT, and the CT here is cost boundary in year 0. Cost boundary in year 0. And then, but when you are multiplying this, the W and the X, your focus is on this X. Is the X your focus is on? Is the X or the Y is the input your focus is on? And so that is why your focus is on the E1 because it has T plus 1 there. But when it comes to where you have CT with certain things in the bracket, your focus is on the CT, is on the one outside the bracket. I'm sure you guys understand.
Yes, Doc.
Good. So on the basis of that, you can pick all the values already from the previous, and then you can now be able to now estimate.
Doc,
Yes.
please, I have a question.
Yeah, go ahead.
So, the DIT into bracket xt plus 1 and then yt plus 1, that particular one, are we looking at it relative to the production frontier?
Which one? This one?
No, the DI,
Oh,
please
this.
come to your right.
Yes, it's
Yes.
purely relative to the isoquant, the production frontier. Purely.
Okay. Okay.
Purely.
Thank you.
No cost, no nothing. Purely.
Okay, Doc.
And
Thank you.
remember that you already even had them when you were estimating the normal cost function. Sorry,
Yes.
technical productivity. That is why we didn't
Yes.
even touch this one. Okay.
Okay.
That is why we didn't even touch this first part, which is the technical change part, because we already know this from the technical productivity.
Hmm.
Yeah. So every
Okay.
aspect of DI, 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 DI that you are seeing here, okay, and you are seeing a couple of DIs, okay, there are 4 of them here. Now watch carefully, if you look at these 4 DIs, watch carefully. Let me show you something. Now look at this one. Do you see the technical change here? The DT, XT, YT. Do you see this one?
Yes.
Now watch carefully. That is the one that is on the far end here.
Okay.
Then this it's diagonal, which is this one, dt plus 1, t plus 1, t plus 1. You see that one here?
Yes.
That is the same thing here at the bottom here. That is the same thing at the bottom.
Yeah.
And then there are cross periods that are above them. For example, look at this one. Okay. T is outside, the t plus 1 is inside. That is what you see here. The t is outside, the t plus 1 is inside.
Yes.
So it is like picking the whole of this, coming to drop them here, but then attaching certain things to it. So the values you are seeing here, you see, watch, OE1 over OB naught is the same thing here. OE1 over OB naught. This second one, OE1 over OE1 is the same thing here. OE1 over OE1. This one, OE0 over OC0 is the same thing. OE0 over OC0. And the last
Okay.
OE0 over OC1 is the same thing. OE0 over OC1 is the same thing on that section.
Okay.
Now, this second part is where you got to understand the cost element part is where you understand. So this is observed cost, which is CT, CT plus 1, CT, CT plus 1. Now, when it is CT, okay, as you can see here, okay, you have what? You have F. And you have to check relative to what is in the bracket, because this one was year 2 relative year 1 relative to year 0. That's why it is OF. Now, when you come to this one, where is that? OJ, OH, OB1. Okay. Now, OJ, it is, even though it has the same CT as the previous one, they are all having CT, but the thing in the bracket was what? Was YT.
Yes.
But the thing in the bracket was what? YT plus 1. So that is why the value here, the letter here is OG. OG because you are looking at the firm in year 0 relative to the frontier, the cost frontier in year 0.
Okay.
Yes. And once you understand that little trick is the most powerful thing and all of that. And don't forget that in this very instance, there was a division. OE1, OE0, OE1, OE0. There was a division before this square bracket. Once you do the substitution, you do the number substitution, and then that will give you the value of the technical change. Now, do you remember that we had the same technical change when we were calculating the Malmquist technical change?
Yes, Doc.
The same technical change here. Now, this is a new price effect, which is 1.046. Okay. And of course, if you take the reciprocal, then you will know that it is exhibiting what? Regress. So let's go back now to the interpretation. Okay. Before I come to this last one, let's go back to the interpretation of the price. This is it. The price effect ratio at the input mix of is 1. Since both E1 and BO are the least cost points in the year 1s and 2 respectively. And the price effect we had is 1.046. It's a regress. If you take the, which shows that the minimum cost, and this is the interpretation very important, the minimum cost of output at the input mix of E has an unbalanced risen. They've gone up between periods 1 and 2. Okay. Now watch the word. The minimum cost has gone up. So it means that cost itself, which is supposed to be minimum, has gone up. So that's not good news. That is why there's a regress. Are you guys understanding it? Okay.
Yes, please.
If you don't take it, you might think that word resin is for the regret. Sorry, it's implying progress. It's not progress. But we are talking about it is the minimum cost which has gone up. And no wonder that is reflected in a price effect regress value. So that is it. Now with all these, let me just go back. With all these, you can now find the final Malmquist. Let's substitute the first one with it. This is the technical and allocative efficiency chain. This whole thing here is a 4-part decomposition. The red and black is a 4-part decomposition. But don't forget that this efficiency, say this TEC here, and then this TC here alone make up the Malmquist. Do you know that?
Yes.
This TEC and the TC make up the Malmquist. And that is why I put the two together. And I still have the AEC, which is there. I still have the PE, which is there. Okay. So this is now, the Malmquist is now, the cost Malmquist is now the actual Malmquist, the technical Malmquist, multiplied by the allocative part, and then and you still get the same value. Get the same value. Now, this is what is interesting here. Why we say the allocative efficiency change is important. If you look at the Malmquist, okay, the value here. Now, the Malmquist value shows that technical productivity has gone up by 114. Do you remember?
Yes.
The cost shows that technical productivity has risen by what? 190 what? Do you remember what you guys said?
139.2.
39.
Yes, 139.2.
So let's say it's gone up by 140%, right? And this one has gone up by 114%. So cost productivity is helping us to see that something is driving productivity by more. And that was what? In this context. Was that a price effect?
No.
Yeah, price effect, no. Okay, it is allocative efficiency change. Now, how is that powerful? It's powerful because even though price effect is bringing things down, even though price effect is bringing decline, the allocative efficiency change was so big enough that it was able to offset the price effect and then help the cost productivity to go up by more than the technical productivity. Do you guys get that one?
Yes, please.
Yeah. So that is why we cannot ignore the allocative element, because in many cases, or in some cases, the allocative part is powerful enough to ginger productivity by a greater percentage. Ladies and gentlemen, this is how you estimate cost productivity. So the cost productivity of 4.16 implies that E has experienced cost productivity progress. E has experienced cost productivity progress between year. Now, this gain, okay, this is very important. Okay. This gain is a bit higher than the standard technical productivity because the cost index shows improvement in allocative efficiency, which wasn't captured by the technical productivity. And of course, all analysis here has been done using the CRS. So one extension you can do is to do the whole analysis using VRS. Now, using VRS simply means that, of course, you have to go and battle and get intuition before. Using VRS means that your technical efficiency, say the TEC and the TC will remain. It will not change. Okay? It will not change. But then VRS will mean that you need to now get split this TEC into two and have pure technical efficiency and then scale efficiency. Do you guys remember? So how do you split this 0.667 into two so that it becomes a 5-part decomposition? Of course, that is a PhD level or even a master's article level thing that you can venture. Okay. And for that to be done, your cost, the intuition must be strong, to be honest, for that to happen. All right, any question? Let's run it. Cost orientation is input orientation, returns to scale. And I'm just going to choose the scale, okay? Just the scale efficiency part.
Okay.
Now, of course, it will tell you that the results are going to be slightly with a different name. Okay. Now, this is a estimation of the scale efficiency part. You can see that it's giving me everything one scale effect. You see that?
Yes.
It's giving me everything one. Now, so for me, what it's kind of telling me is that majority of these data are located in a kind of one section. You know, the data you have now that is just to justify why I had the results which are the same. Okay, this result. Why I had the CRS results to be the same. If you look at it, everything is the same. 1.26, 1.26, 1.33, 1.33, blah 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 blah. All through. Okay. So the possibility is that the data are all similar. Now look at the data. This is the data you gave me.
Yes.
And yeah, almost everything is single digit. So maybe one of the things you want to do is that you want to alter this thing, put some bigger values, 300, 400, 500, 600, 700, okay, you know, single digits, double digits, triple digits. Or even quadruple digits. Single digit, so that it becomes manya, so that if they were to be scatter plotted, they will not be kind of located because return to scale looks more at the location, the location of the data point, so that it doesn't look like they are all located in one region.
Okay.
So you want to get that for us to try, because until we try that, you are just going to make an argument. And what do I mean by making an argument? Let me show you something. Okay, we've been able to detect clearly that there's VRS operating, and so on the basis of that there's VRS. Because mind you, one of the things that we were able to establish was that we didn't use CRS, we didn't use VRS. I know you are not seeing the screen, all right, but we didn't use CRS. Sorry, we didn't use VRS. I just want to be sure, but I don't think we used VRS. Sure of what I'm saying. So let's just see. VRS, this is the first time. The VRS. Malmquist. See, when you go to the actual Malmquist, let me just show you. I just want to see why he spoke about it. Let me start. By measuring their respective constant return. You see this sentence here. blah blah blah, measuring their respective distances from the constant returns to scale production boundary. Did you see that?
Yes.
Okay. An index score that implies productivity regress and constant is significant by an index of 1. And then he says that graphically show that the index gives biased estimate of productivity when they are defined with reference to VRS, even when the production exhibits VRS. Okay. Desley and School measures productivity correctly, okay, using both VRS and CRS. So for me, this is what I wanted to indicate. That if it was estimated, if you did your test, just a second. Come on. Guys, do you understand his question? Or you are just listening? You don't know what.
Please, I think I understood it.
Yeah. Explain.
From what I understood, she was asking whether we should estimate it using the VRS or the CRS. But then with her data set, because it was small, the estimations for both VRS and CRS were the same. And you were saying that because like the data set isn't big enough, for now we should just use the CRS. But if we get a big enough data set and you run it in VRS and we see that the values are different, then we should estimate with VRS.
Good. Yeah. I just want to show something here. The distances, blah blah, are defined as in the, and with reference to the CRS production boundaries. And these people did that. And there was a paper. There's a paper I've read, which also says the same thing that again it keeps happening where blah 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 denotes blah 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 with reference to the CRS technology. So these people that pioneered this, they didn't do CRS, they didn't do VRS, they did CRS. But do you know what is interesting? Here you go. We use the CRS cost boundaries as benchmark. Use that. You see what he said here? At this point, know that at this point that again, we don't need to make assumptions about return to scale. That characterizes the technology. We use CRS cost boundaries as benchmarks for productivity. Okay. So they use CRS. There was a guy who even did a meta frontier. Do you remember the guy who did a meta frontier? One,
yes. One.
He even said that he even extended this thing to the meta frontier and did not also use the VRS. He also went ahead and used the CRS. So for me, I even said I was going to just expand this thing to VRS. But the thing is that if you want to expand the thing to VRS, you have to show it clearly, what the software is doing. But right now, the software didn't give us a good report. The software didn't give us a good report. Let me just show you something what I mean by the software didn't give us. I mean, this is the too many things, Zoom, everything. This is the results we have. And the results here is telling me that the results are the same. Probably because of the data we had, small values and all that. So the only way we can say that there's a difference in the results, and that difference is as a result of skill, is to get a larger data set.
Okay, Doc.
Bigger numbers and you see, let me tell you, the word size means that the word constant returns means that size doesn't matter, isn't it?
Yes.
Constant returns means size doesn't matter. Variable returns means what?
Size matters.
So if you look at these values and look at the values you are giving me, what shows that size matters here? if we are to calculate standard deviation, it doesn't show that some DMUs have bigger numbers and some have smaller.
Okay.
The only way you can prove that VRS is there, size matters, is when there is a bigger standard deviation. Trust me, if I go and do a descriptive statistics for the X1, X2, Y1, Y2, you will see clearly that there's no big differences. What's the big difference? Look at it. The highest number here is 5. And the lowest number here is 1 for the output. Isn't it?
Yes.
So if you find the mean, find the standard deviation. Hey, me, oh yeah, may I okay. See, if you find the mean and the standard deviation, okay, if I should find the bottom here and I type standard deviation, okay, so let me just do some formula. Okay. Let me just even find average of this. The average here is 2.9. Now let me get the standard deviation. Standard deviation, what is it? I don't get the right essay. ST. So here, look at it. The standard deviation is not even above the mean. Do you see that?
Yes, Doc.
One way you can determine that the scale size matters and VRS matters is when it is clear that the standard deviation is above the mean. When the standard deviation is above the mean, here the mean is almost, the standard deviation is 1.17. So the standard deviation is not above the mean. If it's above the mean, then size matters.
Okay.
So trust me, I'm telling you this thing. I'm using my mathematical brain. Go and increase these values, blah, 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 as many as you can. And then send it to me with, one of them is 2, one of them is 2,000, one of them is 3, one of them is 100, one of them is 500, one of them is, okay. Let's do that, maybe, bigger numbers. And then send it and run it again. It will showcase it.
Okay, Doc.
Yes. And of course, that is the essence of VRS, isn't it? So if you're telling me that your non-parametric statistics is going to give you VRS, then it will only also give you VRS if there is a reason for that basis. And if that is the reason for that basis, then your results will also give you a proper result. So work on that and let me see.
Yes, Doc.
And I think that's why the scale change is all constant. Size effect. Okay. Any other question? I hope you guys are learning, because the thesis is on the actual,